6-4, applications of linear systems. So our objective for this section is to choose the best method for solving a system of linear equations. You can solve a system of linear equations using a graph, using the substitution method, or the elimination method. The best to use depends on the forms of the given equations and how precise the solution needs to be. Right? So when you're looking at an equation and you're looking at a system, really you're going to have to decide, can I estimate the answer or do I have to be exact? Okay. So when you graph, this provides you a visual display of the equations, or when you want to estimate a solution. It's not going to be precise because in order to be precise, your graph really needs to be exact, or you need to use some sort of graphing utility like Desmos or some sort of graphing calculator. With substitution, you should use this method when one equation is already solved for one of the variables, or when it's easy to solve for one of the variables, like if x or y is by itself. And with elimination, you should use this when the coefficients of one variable are the same or opposites, makes it easy to cancel something, or when the other two are not any good. So if you can't graph, if you can't use substitution, then elimination is probably your best option. So systems of equations are useful for modeling problems involving mixtures, rates, and break-even points, and we'll look at a few of those in a minute. The break-even point for a business is the point at which income equals expenses. So the graph on the right over here, shows the break-even point for one particular business. So you can see as the number of items that is sold goes up, the amount of money they make goes up, and eventually here they're losing money, but eventually they come to this point where the income line is higher than the expenses line, and that's called the break-even point. And over here is where the business makes money. And that's what this says right here, that the values of y on the red line represent dollars spent on expenses. The value of y on the blue line represent the dollars received as income. So y is used to represent both expenses and income in this example. Okay. So let's look at a problem dealing with finding a break-even point. So a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must the designer sell to break even? So first, let's define our variables. So X is going to equal the number of hats sold. So number of hats. And Y is going to equal the dollar amount. Okay, so now let's write our two equations. One first for my expenses. Well, how much does it cost to make these hats? Well, Y, dollars, is going to equal, let's see, the material for each hat costs $5.50. So this person is going to be spending $5.50, I'll have to put the zero, times the number of hats they make, plus the fixed cost of $1,400 that they spend on advertising. Okay, my income is going to be that each hat makes $12.50 times the number of hats you sell. And because, well, okay, so let's change this a little bit. Let's say that Y is equal to 1250x, right? Dollars is equal to 1250x. Now, because both of these are equal to Y, you can set both equations equal to each other using substitution. So 12.5x is equal to 5.5x plus 1400. Okay. How do I want to solve this? I want to isolate x, so I'm going to subtract 5.5x from both sides. Okay, this will give me 7x is equal to 1400. Divide out the 7, and I get that x is equal to 200. Okay, since x is the number of hats, the designer must sell 200 hats to break even, to make the same amount of money that they spent to recoup this $1,400 investment in advertising. Okay, let's try another one. Our little got it problem. So with the got it problem, a puzzle expert wrote a new Sudoku puzzle book. His initial costs are $864. Binding and packaging each book costs 80 cents. The price of the book is $2. So, same thing. Let's let x equal the number of books. Number of books sold. And then y again is going to be the amount of money that I make or cost. So for my expense formula, okay, my expenses, my initial costs are 864, and it costs 80 cents to make the book. So y is going to be equal to 80 cents times the number of books plus $864. Income is going to be $2. So y is going to be equal to $2 per book. Again, because both of these are equal to y, I can set them equal to each other using substitution. So 2x is equal to 0.8x plus 864. I'm going to subtract 0.8x from both sides to give me 1.2x is equal to $864, or just 864. Divide by 1.2. And that gives me that x is equal to 720 books. Okay? All right, so in real world situations, you need to consider the constraints described in the problem in order to write the equations. Once you solve the equation, you need to consider the viability of the solution. For example, a solution that has a negative number of hours is not a viable solution. In our first two problems here, 200, that's a viable solution. You could make 200 hats. And for the got it problem, you could print 720 books. Those answers make sense. They are numbers that work. Okay. If maybe in the next problem, if we get a negative number of hours for a time that something is going to happen, that would not be a viable solution, which means the system has no solution. So next problem here, identifying constraints and viable solutions. So the local zoo is filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons an hour. When will the 2 tanks have the same amount of water? So let's define our variables first. X is going to be the number of hours, okay, number of hours to fill up the tanks. And y, let's let y be gallons. Okay, so let's write an equation for tank 1 and tank 2. And then we'll figure out how to solve them. So the gallons for tank 1 is going to be equal to, so let's call this our first water tank, 50 gallons, 10 gallons an hour. Okay? So it already has 50 gallons in there when I started. So the number of gallons that the tank has now is going to be 10 gallons times the number of hours plus 50. Tank 2 contains 29 gallons at 3 gallons an hour. So Y is going to be 29, whoops, let's write this the other way, let's keep it the same. So 3 gallons an hour plus 29 gallons. The question says, when will the two tanks have the same amount of water? So since I made equations that are both equal to Y, and since I want to know when these two things are going to be the same, I can set them equal to each other. Okay, let's get a little more room here. So subtract, whoops, subtract 3x from both sides. We have 7x over there plus 50 is equal to 29. Subtract 50 from both sides, and I have 7x is equal to negative 21. Divide out the 7, so x is equal to negative 3. Okay, a little weird, but if I plug negative 3 back in, y is going to equal 10 times negative 3 plus 50. So that is going to be negative 30 plus 50. So y is equal to 20. So basically what this answer says is that x is equal to negative 3, y is equal to 20. Let's go back and look at my problem. X is the number of hours. So in negative 3 hours, these two tanks will both have 20 gallons. So that answer does not make sense. So there is no solution to this system since you can't go back 3 hours in time. So these two tanks never have the same amount of water. And if I think about it logically for a minute, that's got more and fills faster. So it's not possible to have a tank that starts with a lower amount of water and fills up slower than the other one ever have the same amount of water in them. Okay, so this problem has no viable solution. Even though we did get a solution, there is a place where these two lines intersect. There is a time when they have the same amount of water. It's just not a time that we can work with. Let's look at another one. So the same zoo has two other water tanks that are leaking. So one tank contains 10 gallons of water and leaking at 2 gallons an hour. The second tank contains 6 gallons of water and is leaking at a constant rate of 4 gallons an hour. When will the tanks have the same amount of water? Well, let's do it. So x is going to be equal to hours, and y is going to be equal to gallons. Okay, so let's break this down again with tank 1 and tank 2. Now, the number of gallons is going to be equal to 10 gallons of water, but instead of adding this, it's going to be losing 2 gallons an hour. So we're going to be subtracting it. And the same thing in this, y is going to be equal to 6 gallons minus 4 gallons an hour. Again, I can set these two equal to each other. So 10 minus 2x is going to be equal to 6 minus 4x. Let's go the other way so we can keep x positive. Let's add 4x to both sides. So I have 2x. Let's bring the 10 down. 10 plus 2x is equal to 6. Subtract out the 10. Let's get a little more room. And we have 2x is equal to negative 4 which means x is equal to -2. Okay? And x, again, is the number of hours. So I don't even want to plug this back in. Uh, uh, my answer here is going to be a negative amount of hours. Okay, so that's when these tanks would have had the same amount of water in them. But that's the solution for the basic problem. But I guess we can kind of argue this one a little bit and say that since the tanks are losing water, this first tank is going to take the longest to lose water, and in 5 hours, it's going to have no water in them. This tank will already be empty. So if we really wanted to get like technical, we can argue that these tanks will have the same amount of water in them in 5 hours because they will both be empty. That's not really what the textbook was going for here, but I thought that was interesting to mention. Okay, let's look at one more type of problem here where we're looking at a plane. So when a plane travels from west to east across the United States, the steady west to east wind acts as a tailwind. It's called the jet stream. Always goes west to east. Sometimes it dips down a little bit more as it's traveling across the country, but it always goes from California to New York across the country from west to east. So now that means when you're flying from California to New York, or in our next example, North Carolina, as you're flying from west to east, you're going to go faster because the wind is at your back. It's going to push the plane faster, just like in this graph right here. So the airspeed plus the wind speed equals the ground speed. The opposite of this is also true. If you fly into the wind, you go slower. So the airspeed minus the wind speed is equal to your ground speed. So in both of these cases, the airplane is going the same speed, but here the wind is helping it, making you go faster. Here the wind is hurting it, making you go slower. All right? So this works for a problem with wind like this, or a current, which we'll look at in our got it problem. Same sort of idea, except now you're going in a stream, like a body of water. So a traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same. If the ground speeds are shown below, what is the speed of the air? Okay, so let's set up a few equations with the first plane and the second plane. Let's not use x. Okay. All right, so we have our airspeed plus the wind speed is equal to the ground speed. And the same thing here, the airspeed, but now you're going against the wind. So minus the wind speed is equal to the ground speed. All right, well, we do know one number for both of them. So the airspeed plus the wind speed is equal to 550. The airspeed minus the wind speed is equal to 495. Well, I'm not trying to find when they're equal to each other. All I want to do is solve for both of them, but luckily I have two equations, a little bit more room here. I have two equations, and if I notice, one has a positive W, one has a negative W, so I can solve this using elimination. So A plus W is 550. A minus W is 495. If I add these two equations together, I get 2A is equal to 1045. Divide out the 2 to give me my airspeed of 522.5. And we're talking about miles per hour in this case. Well, that's great, but that's not what the question actually asks for. The question says, what is the wind speed? So I could have solved for that first, but it was much easier just to cancel these two out than to try to mess around with canceling A out. So I solved for A, and now all I have to do is plug it in. Either equation is fine. Let's do this one so we have a positive number. So that's 522.5 plus W is equal to 550. Just subtract off the 522.5, and W is equal to 27.5. And that's still in miles an hour. Okay? So we have my airspeed right here and my wind speed right here. Not bad. Kind of fast for the wind, but as you get higher and higher, the wind actually, the wind speed can get up a little bit faster than you're used to on the ground. All right, let's try. I got a problem, and then we'll wrap it up. So we row upstream at a speed of 2 miles an hour. You travel the same distance downstream at a speed of 5 miles an hour. So here, and we can use the same equation, except instead of airspeed as A, let's call it water speed plus the current. I'm sorry, water stream. Upstream means you're fighting against the current. So water speed minus the current is equal to 2. And water speed plus the current is equal to 5. And again, the best way to solve these is with elimination. So I'm just going to move this second equation over to there. Water speed plus the current is equal to 5. So that's 2W equals 7. Divide out the 2. So W is going to be equal to 3.5 miles per hour. And the current, let's use the positive one again, this one right over here. So that's 3.5 plus the current is equal to 5. Subtract it off. And the current is equal to 1.5 miles per hour. And usually with a good current problem like this, the speeds are going to be much closer than with an airplane and the wind speed. Suppose your rowing speed in still water is 3 miles an hour. The speed of the current is 4 miles an hour. What happens when you try to row upstream against the current? Well, if you can only go this fast, but the current is pushing you faster away, you are not going to be able to go upstream. It's going to push you back downstream. You're going to be going -1 miles per hour, which means you're going to be going backwards. So turn around and go the other way. All right, so let's wrap this up. Our quick lesson check here. Printing newsletter. These three, I don't want to do all three, but we can set up a little bit here. Printing newspaper costs $1.50 for copy, $450 in printer's fees. Copies are sold for $3 each. How many copies of newsletter must be made to break even? So that's 3x is going to be equal to 150x plus 450. There's my setup, and we can solve that. Metal alloys made by blending 2 or more types of metals. A jeweler has supplies of 2 metal alloys. One is 30% gold, the other is 10% gold. How much of each alloy should the jeweler complain to get 4 kilograms of alloy containing 15% gold? So we're just going to set up the same sort of equation here. Don't get confused by these, right? Just change them to decimals. So when we set it up, 30% gold, the other's. So when we set up, we're just going to use 0.3 and 0.1 for each one of those. And with the flying problem, same thing is that we just did bird flew at a ground speed, flying the same path against the wind. So we have ground speed, sorry, with the wind, there we go, tailwind, and with the wind. So tailwind means it's going to be going faster, and against the same wind means it's going to be going slower. So just for look for those sort of cues to tell you which way which one is going faster, which one is going slower. Tailwind's a good word. With the wind, with the current, anything like that that explains direction. Relationship between income and expenses before the break-even point is reached. Before you break even, you're going to be losing money. Afterwards, you're going to be gaining money. Usually a relationship with a profit-loss graph is not going to be as simple as two lines crossing. It's going to probably be more complicated than that. For 5, which method would you use to solve the following system? Well, if you look at this, don't cancel, don't cancel. So I would use uh, there's no variable by itself. So I would use elimination, but it's not going to be an easy elimination. You're going to have to multiply the top and the bottom by something to make them cancel. Probably, I would multiply the top by 2 and the bottom by 3 and make both of these a 6 and cancel out. Okay, and the last one, similar to number 2 over there, one brand of cranberry apple drink is 15% cranberry. The other is 40%. You like to combine the brands, so just add them together. Which brand of juice, without calculating which brand of juice will you need more of to make your drink? Well, if you got this one and you got this one, okay, and you want to make it higher, you're going to need more of the 40% juice because you want to make the cranberry juice stronger, as opposed to if you start out with that one, you're going to make it weaker. If you have more 15% juice, you're going to make it weaker. Actually, I take that back. Um, if we find the middle of it, let's think about it this way, okay? I was thinking about adding one juice to the other one. That's not really what this question says. It says if you combine them, so halfway between 40 and 15 is 27 and a half, okay? So if you had an equal amount of juice and you mix them together, you would have 27.5%. So you need more of the 15% juice. So wrong, right, there we go. All right, and that was success for applications of linear systems.